Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the waning years of the 19th century, a pervasive sense of completeness settled over the discipline of physics, the grand edifices of Newtonian mechanics, Maxwellian electromagnetism, and the laws of thermodynamics appeared to offer a comprehensive and deterministic account of the material world. The few remaining anomalies, such as the peculiar glow emanating from evacuated glass tubes, were viewed by many as minor puzzles to be tidied up within the existing paradigm. It was from within this context of confident finality that a single, unassuming publication emerged from the University of Würzburg, a document so potent in its empirical clarity that it would shatter the prevailing scientific complacency and inaugurate an era of revolutionary discovery. Wilhelm Conrad Röntgen's 1895 preliminary communication on a new kind of rays stands as a monument to methodical observation and serendipitous inquiry. It is an archetype of the scientific paper as an instrument of radical change, a work whose sparse, cautious prose belies the seismic intellectual shifts it would trigger, ultimately laying the foundational stone for the physics of the 20th century. This essay will explore the genesis of Röntgen's discovery within the fertile ground of cathode ray research, dissect the stark and rigorous experimentalism that defines his paper, and trace its immediate, explosive impact and its profound, enduring legacy as the catalyst for the atomic age. Röntgen's breakthrough was an outgrowth of a vibrant and highly competitive field of experimental inquiry focused on the strange phenomena observed during electrical discharges in rarefied gases. The intellectual groundwork had been methodically laid by a generation of European physicists. The investigations of Julius Plücker and his student Johann Wilhelm Hittorf in the 1860s first identified the strange emanations from the cathode. Sir William Crookes, with his masterfully crafted high vacuum tubes, elevated these observations into a spectacle, proposing that cathode rays constituted a novel fourth state of matter, a stream of charged particles. Yet, the definitive step towards Röntgen's work was taken by the Hungarian-German physicist Philipp Lenard. Building upon the insight that cathode rays could induce fluorescence, Lenard devised a Crookes tube with an exceptionally thin aluminum window. This Lenard window permitted the cathode rays to escape the confines of the glass tube for the first time, allowing for the study of their properties in the open air. Röntgen, a meticulous and deeply respected experimentalist, was engaged in replicating and extending Lenard's work in his Würzburg laboratory. He was operating within a well-established research program, employing its standard apparatus, the Ruhmkorff induction coil, to generate high voltage, and a Crookes or Lenard tube to produce the cathode rays. His discovery, while accidental in its initial trigger, was the product of a prepared mind steeped in the precise traditions and unresolved questions of this specific domain of ink. The paper itself, Ein Art von Strahlen, Vollständig, Mitteilung, submitted on December 28, 1895, is a masterclass in scientific reticence and empirical rigor. Its power resides in its unadorned presentation of observation, a deliberate avoidance of speculative theorizing. Röntgen describes the pivotal moment on November 8, 1895, when, working in a completely darkened room with his cathode ray tube shrouded in black cardboard, he noticed a faint, shimmering light on a nearby bench. The source was a small screen coated with barium platinocyanide, a material known to fluoresce. This was unexpected. The opaque cardboard should have blocked any known form of radiation, including the cathode rays themselves, whose range in air was a mere few centimeters. What followed was a period of intense, secretive, and brilliantly systematic investigation. Röntgen's communication proceeds as a numbered list of observations, each building upon the last with irrefutable logic. He first established that the source of this new agency was the area on the glass wall of the discharge tube struck by the cathode rays. He then systematically tested the penetrative power of these unknown rays, interposing a series of objects between the tube and his fluorescent screen. He found they passed through a 1,000-page book, a thick block of wood, and sheets of tinfoil. Lead, however, proved substantially more opaque. This differential absorption was the key to their utility. Most famously, he describes holding his hand in the path of the rays. He witnessed on the screen the ghostly, darker shadow of his bones within the fainter shadow of his flesh. To document this incredible finding permanently, he replaced the fluorescent screen with a photographic plate, producing the iconic image of his wife Anna Bertha's hand, her wedding ring a stark, impenetrable shape on her skeletal finger. This single image conveyed the discovery's power with a visual immediacy that transcended the technical language of physics. Crucially, Röntgen also reported that a strong magnet, which readily deflected the stream of cathode rays inside the tube, had no discernible effect on this new radiation. This observation established the new rays as a distinct phenomenon. His choice of the name X-strahlen, or X-rays, was a candid acknowledgement of their mysterious nature, a humility that stands in stark contrast to the discovery's world-altering implications. The global reaction to Röntgen's paper was immediate and electrifying. The news, first reported in the Viennese press in early January 1896, spread via telegraph across Europe and the Atlantic with a speed unprecedented for a scientific finding. The discovery's power lay in its democratic reproducibility. Any reasonably equipped physics laboratory possessed a Crookes tube and an induction coil, and within weeks, researchers around the world were confirming Röntgen's results. The finding escaped the confines of the laboratory with equal swiftness. The medical community grasped its potential almost instantaneously. Physicians and surgeons saw a tool that could render the interior of the living body visible without invasive surgery. By February 1896, doctors in Europe and the United States were employing X-rays to locate bone fractures, diagnose diseases, and find embedded bullets and other foreign objects. This direct, tangible benefit to human welfare gave the discovery a public profile and a level of cultural resonance rarely afforded to advances in fundamental physics. Its visual and slightly macabre nature, the ability to see one's own skeleton, captured the popular imagination, spawning a torrent of newspaper articles, cartoons, and even commercial ventures of varying repute. For a brief period, the X-ray became a cultural phenomenon, a symbol of scientific modernity's power to pierce the veil of the visible. Beyond its immediate celebrity and practical applications, the true legacy of a new kind of rays resided in the new avenues of fundamental research it opened. It acted as a powerful intellectual stimulant, forcing a re-evaluation of the nature of radiation and matter. The most direct scientific progeny of Röntgen's work was the discovery of radioactivity by Henry Becquerel in 1896. Intrigued by the production of X-rays from the fluorescent spot on the glass tube, Becquerel hypothesized a connection between phosphorescence and these penetrating rays. He began testing various phosphorescent substances to see if they, after exposure to sunlight, would emit X-rays. His experiments with uranium salts yielded a stunning result. The salts emitted penetrating radiation continuously, without any external stimulation from sunlight. This radiation, like X-rays, could fog a photographic plate through opaque paper. Becquerel had stumbled upon natural radioactivity, a phenomenon born directly from his attempt to understand the mechanism behind Röntgen's discovery. The cascade continued. In Cambridge, J. Stuart Thomson recognized that X-rays provided an ideal tool for studying the fundamental properties of electricity. By using X-rays to ionize gases, making them electrically conductive, he could perform precise measurements on the Chargaff-Thomas ratio of the cathode rays that produced them. These experiments, conducted in 1897, led him to the monumental conclusion that cathode rays were composed of tiny, negatively charged particles, which he called corpuscles, now known as electrons. He had discovered the first subatomic particle, and in doing so, he demolished the age-old concept of the indivisible atom. The field of inquiry ignited by Röntgen and Becquerel also captivated Marie and Pierre Curie, whose painstaking work isolating polonium and radium from uranium would further illuminate the complexities of the atomic nucleus and the nature of radioactive decay. Furthermore, the long-standing debate over the fundamental nature of X-rays, their resistance to deflection by magnetic fields, left physicists puzzling whether they were a form of wave or a stream of neutral particles, was itself immensely productive. The question was finally settled in 1912 when Max von Laue, Paul Knipping, and Walter Friedrich demonstrated the diffraction of X-rays by a crystal lattice. This experiment confirmed the electromagnetic wave nature of X-rays, placing them on the spectrum alongside visible light but with a much shorter wavelength. It simultaneously gave birth to the powerful analytical technique of X-ray crystallography, a tool that would later be used to unravel the structure of DNA and countless other complex molecules. In conclusion, Wilhelm Conrad Röntgen's 1895 paper on a new kind of rays represents a pivotal moment in the history of science. It was a work born from the established experimental tradition of cathode ray physics, yet it transcended its origins to become a revolutionary force. Its genius lies in its profound simplicity and unwavering dedication to empirical evidence. Röntgen offered no grand theory, merely a sequence of meticulously documented, undeniable facts. These facts, however, were potent enough to dismantle the edifice of classical physics, which had presumed a world fully accounted for. The invisible rays he unveiled offered the first glimpse into a subatomic reality, a world governed by principles yet to be conceived. The paper's immediate legacy was twofold. It provided medicine with a diagnostic tool of incalculable value, and it handed physicists a key that would unlock the atom from the eerie glow of a barium platinocyanide screen in a darkened Wuersburg laboratory a chain reaction of discovery was initiated that led directly to radioactivity, the electron, and the entire conceptual framework of quantum mechanics and nuclear physics. Röntgen's communication was more than a report on a new kind of ray. It was the quiet announcement that a new and far stranger reality awaited human exploration, a reality that could be perceived only by looking straight through the surface of things.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.